measurements, or is it somehow built into the way nature is? That's the big question, right? Now, a lot of people, many people think that it's just inherent. It's just the way nature is. It's just this basic, inherent, unremovable fuzziness about the nature of these quantum systems, these wavicles. Like, do you have to give up the idea of a trajectory, like a path that an elementary particle, for example, takes? Now, if you perform, in a sense, a kind of continuous measurement, like the particle physicists, before they had bubble chambers. And what's that? Well, it's a volume filled with hydrogen gas, but what's the word? It's almost, it's at a temperature such that it's almost on the point of condensing into a liquid, right? It's on that, like at that critical threshold temperature, and shooting particles through it creates a kind of trail in the hydrogen gas that acts as a sort of seed. It's like a line of seeds, if you like, and hydrogen bubbles form and create little droplets of hidrogen liquid, right? So you get this trail, and so that way you, like if you these elementary particles, you're placed in electric fields and magnetic fields, they'll bend and spiral, and judging by the strength of the fields, you can figure out the mass and the speeds of these particles and so forth. So very useful device in particle physics. I mean, nowadays the technology is more modern, tend to use spark, so use electronic techniques, spark chambers and so forth. And I'll be talking about all this stuff in particle physics courses that I'll be giving. I will give a particle physics course even at undergrad level. Expect one in, I don't know, sometime within a year or less. I'll definitely give a particle physics course at undergrad, and then at all the way up, M1, M2, PhD 1, 2. So particle physics, really important for quantum for physics, theoretical physics. All right. So these bubble chambers and spark chambers and so forth. The particle physicists, they just seem to think of, well, they talk about particle physics, right, rather than wavicle physics or wave physics. For them, because in a sense they're observing all the time, it's sort of like a continuous measurement, and for them, they tend to see trajectories, paths taken by these particles. But the problem is when you perform a measurement, and I'll talk about that a little, something called collapse of the wave function. If you're doing a continuous your wave function, in a sense, collapses all the time, and hence you do tend to get a trajectory, a path. Now, I'm probably confusing you like crazy. Welcome to quantum mechanics. The subject is indeed confusing. It is full of philosophical, deep philosophical questions about even the nature of reality. There's a lot of metaphysics in it. There's a lot of epistemology. What can you know? The philosophers of science have had a field day with quantum mechanics. There are just so many interesting philosophical questions in that topic. Unfortunately, physics itself, mathematical physics, has now advanced to such a point. The mathematics that's now used in modern, at very advanced, highly advanced PhD 2 level theoretical physics is well beyond the knowledge level, and to some extent even the intelligence of a lot of these philosophers of quantum mechanics. So they've more or less dropped out of attempting to analyze the latest stuff in math physics. But I'm hoping you guys will stick with me, and I'll take you right through PhD 2 stuff. And who knows, maybe some of you may tackle the latest questions on interpreting nature, quantum mechanics, using these latest math techniques. Now, let me say this. as far as physics knows, like the most powerful atom smashing machine today is the LHC. That's the Large Hadron. Hadron just means a heavy particle. Large Hadron Collider in Geneva, Switzerland. It's right on the Swiss-French border. Now it can accelerate protons up to an energy, well, not yet, but that's the plan. I mean, they're increasing it in increments year by year. They will take up the energy to, if I remember correctly, 14 GeV. That's giga electron volts. So one proton will have up to 14 GeV. Now, with some elementary physics, fresher level physics, you can calculate then the wavelength, the de Broglie in French, wavelength of that proton. And I think, well, I haven't done it, but I think you'll come out at something like 10 to the minus 18 of a meter. And quantum mechanics seems to be valid all the way, experimentally, right down to those tiny scales. So even 1,000 times smaller than the nucleus, smaller than quarks, and this kind of thing. So incredibly small. And if you think about it, quantum mechanics, string theory at 10 to minus 35 of a meter is based on quantum mechanics. And all kinds of amazing predictions have come out of string theory already. For example, general relativity, the theory of general relativity just drops out as a deduction from string theory. And string theory predicted supersymmetry. And supersymmetry, we hope, now that very recently the Higgs boson was discovered by the LHC, great celebration, just literally days ago, so you can judge when this particular video was made. It was only a few days ago, the wonderful discovery that finally the Higgs boson has been confirmed officially to 5 sigma, meaning 5 standard deviations of chance, so by definition discovery in official terms. So it looks like the next thing the LHC will be hopefully discovering will be supersymmetry, and which is sort of, there's a kind of symmetry between fermions and bosons. Don't worry about it. We'll cover this stuff in particle physics. Even at undergrad level, you'll know what difference between bosons and fermions are. But there's a symmetry between those two. And even all that theory still relies on quantum mechanics. So it looks as though quantum mechanics is valid like all the way down. So even starting from 10 to the minus 18 of a meter, which is the experimental limit that we have today. But string theory and brain theory, that goes right down to 10 to the minus 35 of a meter. That's the smallest scale that humanity even has theories about, right? And it looks as though quantum mechanics is valid even at those tiny scales, because string theory is based on quantum mechanics. So maybe this uncertainty, this fuzziness of the behavior of waves and particles is built into nature, and it may go all the way down. So maybe there just, as far as we know, there just isn't any sub-quantum. There just isn't anything lower. So it's certainly looking that way, given the validity of quantum mechanics in string theory. Now, speaking of string theory, I will, that's certainly my plan. I mean, I want to master this topic to a large extent myself. That's one of my goals in my retirement. Well, sort of my arcing, A-R-C, that's after retirement careering. So my new career is, I'm teaching myself all this mathematics and physics to understand string theory and such, and then once I understand it, to pass it on to you in the form of a permanent record that just stays on the internet for decades. So I hope it will become a wonderful resource in the future. All right. Okay, so so this big open question. So this fuzziness, this uncertainty, like in the position of a particle or its momentum and so forth, the HUP, is it due to clumsiness about tools or somehow inherent? All right. Now let's sort of move on a bit. Been rambling somewhat. So the Young double slit experiment, the setup is as follows. You have a source here, a source of, let's say, light waves or water waves or sound waves, whatever. You have some sort of impenetrable, cannot be penetrated barrier here, except for two slits. Like here's an impenetrable barrier, and you have two vertical slits, like gap that the waves can pass through. Right? So the waves pass through these two slits. And then here on the right hand side you have a detecting screen of some sort. Like for example, let's say the source here is, I'm going to make it a little bit cooler just a minute. I wouldn't be at all surprised. It is now the hottest day of the year. I'm in the southeast Chinese city of Xiamen. So it gets pretty warm, and it's now middle July, which is the hottest part of the year. It's right in the middle of summer, so it's getting damn hot. So I have the air conditioning on, even if it's a little bit noisy, but no choice. Sorry, folks. Okay, so you now have a source of water waves. So here maybe you have a little cork here, like a champagne bottle's cork here, and it's bobbing up and down, and it's generating waves, that spread out here. And these waves, they go through these two slits, and then these two waves interfere with each other. Like I take a particular point, let's say, or say in the middle here. So the distance between this slit and this point is equal to the distance between this slit and this point. And so you'll have two peaks of the wave from wave 1 and wave 2. So like two peaks will arrive at the same time. And so you get a kind of double peak of the wave at this point. And then if you move slightly up or down, you might get a peak of one wave arrive at the same place at the same time with a trough, the bottom part of the second wave. So they cancel out. So you get no wave like here and here and here and here. So with two water waves like this, you get an interference pattern, right? Like the sum of wave 1 plus wave 2, right? So you get, because you've got like two waves, and each of them waving up and down. So at different points along this observer screen here, you'll get interference. The two waves will influence each other. So you might get a double up or double down. Okay. So you get an interference pattern, and that's what Young observed with light. Right. So when your source now is just light, sending out light waves in a sense, you got this interference pattern, and like this would be like. If you look at this screen, these regions here would be white. That's where the light came, and these regions in between would be dark. No light there, right? So, and that interference pattern is characteristic of waves, right? That